Internet of Things. And here's something special remarks. So he will graduate in 2024 spring, and he's looking for a PhD opportunity starting in 2024 fall. Okay, the podium is yours.
Okay, so good afternoon, everyone. My name is Lihao Wang, and today it's my honor to present my work, MagSound Magnetic Field Assisted Wireless Earphone Tracking. We believe that wireless earphones have the potential to be a novel HCR input tool. We can sense the movement of earphones by transmitting acoustic signals using wireless earphones and analyze received signals at smart devices. Here are 3 advantages. First, acoustic sensing has a much larger sensing area than touchscreen, so it may have little problem of the so-called fat finger. Second, acoustic tracking can achieve millimeter-level accuracy. Third, wireless earphones are ubiquitous without additional hardware cost. Here we list 3 potential applications, including fine-grained drawing, handwriting input, and VR gamepad. There are mainly 2 challenges before we adapt wireless earphones as an input tool. First, since the smart device and the wireless earphone have their own clocks, they are distributed, their clocks are unsynchronized, so this would accumulate error rapidly for acoustic ranging, which is disastrous for fine-grained tracking. The red line in figure A shows the clock offset between a smartphone and a wireless earphone. A traditional method for this problem is called linear calibration. That is, at the beginning of each round, they fix the positions of the 2 devices individually, take several seconds to record the signal, and compute the average offset between 2 frames. Then, during tracking, they compensate this average offset as a constant. We also draw the results of linear calibration by yellow line in figure A. As we can see, after 4 minutes, there is an offset equal to more than 3 centimeters error. Second, the signal transmitted by the earphone is much weaker than common speakers. Figure B compares the signal strength between a smartphone, Google Pixel 4, and other 3 different wireless earphones. We can see that the signal transmitted by the wireless earphone is much weaker. However, we also see opportunities. Earphones are magnetic. As figure C shows an example of wireless earphone structures. Actually, most wireless earphones have magnetic components to produce sound. So in MagSound, we seek magnetic sensing to solve these challenges. This figure shows an overview of the proposed system MagSound. For the first challenge, clock offset, our key insight is that the built-in magnetometer in the smart device shares a clock with microphones, which is free from clock offset. We train a neural network that inputs magnetic field strength and outputs magnetic coordinates. Then we can use these magnetic coordinates to calculate the clock offset. For the second challenge, the weak signal, we take this sequence as our transmission acoustic signals. We mitigate the noise interference through signal correlation, and the nice properties of the DC sequence allow us to separate signals propagating through long offside paths from multipaths. Further, we model the clock offset as a nonlinear function over time and use the recorded offset to refit the function on the fly, which effectively improves the calibration accuracy. We also design a coordinate fusion algorithm to better utilize the 2 modalities. To study the feasibility of using magnetic field to assist earphone tracking, we measure the magnetic field strength of the earphone using the smartphone's magnetometer. Figure A shows our measurement setup. Note that there are 3 axes in the smartphone's magnetometer, and we can get Bx, By, and Bz 3 strands from the 3 axes. Figure B, C, and D shows the distribution of magnetic field. We call the area where magnetic field strength is significant the magnetic effective area. In MagSound, we use a data-driven method to obtain magnetic coordinates. To remove the background magnetic field, we take a point on the grid as a reference point, and we eliminate the influence of background magnetic field by subtraction. Our dataset takes the magnetic field strength as input and the grid point coordinate as a label. So we compare 3 different machine learning models and finally choose neural network model as our final model due to the low error size and the inference time. For acoustic sensing, we transmit the DC sequence in an OFDM manner using wireless earphones. We list two main advantages of the DC sequence. First, the power of DC sequence is stable and thereby reduces requirements for earphone quality. Second, DC sequence has a good autocorrelation function and cross-correlation function, which would help us determine the phase shift. Figure A shows the autocorrelation of the DC sequence without noise, while Figure B shows the autocorrelation of the DC sequence with an SNR equal to 0 dB. We can see that the main peak is clear and distinguishable in both figures. So in MagSound, we model the clock offset function as a nonlinear function. It is different from previous work. For example, we can model it as a quadratic function. When the earphone is detected inside the magnetic effective area, we record the clock offset and re-estimate the offset function once it moves outside the area. We observe that for magnetic coordinate, it is free from clock offset, but its effective range is limited. While for acoustic coordinate, it suffers clock offset but has a much larger sensing area. Both of the two modalities can achieve millimeter-level accuracy in their effective area. So based on our analysis of the two modalities, we design a fusion algorithm which can be summarized as two steps. First, we calibrate acoustic coordinate and then calculate the displacement between two adjacent frames. Second, we add the last fusion coordinate with the displacement as a new fusion coordinate. Here we present qualitative results for MagSound. We use wireless earphones to draw three shapes, including rectangle, triangle, and circle. The ground truth is drawn in red lines. For each shape, we draw the traces for 4 times and calibrate the clock offset at the interval. We draw the traces of MagSound in blue lines. We also compare MagSound with linear calibration, denoted by one shot, which takes the clock offset as a constant and compensates it linearly. We draw the result of one shot in yellow lines. We can see that the traces by one shot get distorted and drifted over time, while the traces by MagSound keeps relatively stable. As a case study, we evaluate MagSound for handwriting input. We invite volunteers to write 26 uppercase letters using the earphone, and each letter for 16 times. We use an API provided by Google to recognize letters from traces. Figure A shows the overall recognition accuracy. We can see that the accuracy for MagSound is higher than or equal to one shot on every letter. Figure B shows the recognition accuracy over time. We can see that MagSound maintains a high accuracy while one shot drops over time. Figure C illustrates that the MagSound is robust to different writing habits. We also adapt MagSound for fine-grained drawing. We can see that Figure B shows a result of MagSound. Compared with a smartphone touchscreen shown in Figure C and D, the traces by MagSound keeps details and smoothness at the same time. In summary, we make the following contributions in this work. First, we perform the fusion sensing based on the pros and cons of the magnetic and acoustic modalities. Second, to the best of our knowledge, we are the first to make on-the-fly clock offset corrections by wireless earphones. Third, we implement a prototype of MagSound and evaluate comprehensively, including case studies on handwriting input and fine-grained drawing. I am looking for a PhD position in 2024 fall, so if you are interested, please check my homepage for more information or contact me through the email. Thank you. I am available at the panel discussion for Q&A.
Thank you for great presentation. Do you have a question?
Great presentation. It's less of a question, more of a comment. At the beginning of the talk, you said that the acoustic signal would not suffer from fat finger problem as compared to the touchscreen. Fat finger problem is not a sensor problem, it's a human problem. So it's really the limitation of our motor capabilities. So just keep that in mind. And one clarification, when you showed the results, the touchscreen, I'm assuming that the users were using their finger?
Yeah.
And for the sound one, they were holding?
They hold the earphones.
Yeah. So there might be some correlation between that thing, right? Because when you have your thumb as well as index finger, the motor capabilities are much more finer as compared to if you're just using your index finger. So there might be some interaction with human capabilities and sensing here. But I'm happy to talk more about that later.
Okay, thank you.
All right. Thank you for your presentation. All right, and then let's move on. Our fifth presentation will be done by Yongkwan Hu, who goes by Wang. And Yongkwan is a third-year PhD student at CSC, the University of New South Wales, Australia. His research interest includes human-computer interaction and ubiquitous computing, specializing in creating AI-driven interfaces based on both hardware and software. And he